Hi, I'm Christina and welcome back to another one of my cancer translation videos. And in this one, I'm going to continue from my last video where I was talking about cancer treatments. This one's going to be all about chemotherapies, and we're talking mostly in this one about the new chemotherapies, which are targeted therapies and immunotherapies. And so I am going to be definitely translating what would normally be a lot of very, very big words for you into simpler terms, because this stuff gets super complicated. So I know I left this up from the last video, so I'm going to do a little brief recap. So, the old chemotherapy that we used for so long was called cytotoxic chemotherapy, and we still use it to this day. But this was the traditional stuff that we used for forever and ever. And cytotoxic means cell killing. And what that stuff did and still does, is it went after cells that rapidly divided and reproduced. We know cancer cells do that. That's what cancer cells do. They reproduce rapidly. But so do other cells in the body, right? And so that's why you got so many side effects with those. That's why people lost their hair, because the cells at the base of the hair shaft or the base of the hair follicle divide really, really rapidly. So those would get targeted by the chemotherapy. So would the cells in the lining of your stomach, because those reproduce and get turned over really rapidly too. Same thing with the cells inside your bone marrow, because bone marrow, like I said in another video, your bone marrow is your blood cell making factory. So you're creating new blood cells rapidly all the time. So there again was another place that chemo was going, ooh, there's rapidly dividing cells, and killing them, because it just indiscriminately would kill, or does kill, rapidly dividing cells. And so that's why you get all these extra side effects with those old school cytotoxic chemotherapies. Now, the thing is, they do their job well. We have great drugs to manage the nausea, and we even have some stuff to help with the low blood counts these days. Even have a couple of things that can help a little bit with the hair loss now. So we can manage these side effects. And even though everybody still thinks that if you get chemo, you're gonna throw up your guts and lose your hair and turn into a toothpick and weigh 80 pounds. And this is not true anymore. We really can. I'm not going to say you're not going to get sick and be nauseous maybe and be fatigued, but you're not going to be sick like you used to be. We can manage side effects. So this is much better, which is good, because we still need to use these drugs. We combine them with our new drugs now. But those are what I call here on this picture, the old school drugs. That's what everybody has been getting for eons. Those are the cytotoxic drugs that we first came up with to treat cancer. Now, the new drugs are what we call targeted drugs. And that's what in this last video I called the new hotness, the cool stuff. This is the stuff that like I said, people like me are geeking out on right now. This is what we're studying. This is what we're going after. Because the idea is, what we want a drug we can give somebody that goes after just the cancer cells and kills just the cancer cells and doesn't kill anything else. I mean, that's the ideal, right? And so we've been wanting to do this for a long time, but we didn't really know how to do it. And so late 90s, I believe it was. I'm gonna have to go check that one out to be sure. I might have to add something here, but I think it was late 90s. We developed the ability to create monoclonal antibodies. Now, I won't say that too often. Let me tell you what that is. You've all heard of antibodies. Well, antibodies are things that are able to go after and grab bad things in your body. So we made it so that we can create or engineer our own antibodies, and that we can send after stuff. So let me rephrase that entirely. Basically, what we did was we engineered our own cadaver dog. Or actually, it's not even a cadaver dog. It's like a search and rescue dog. Basically, we engineered this little molecule, and when we engineer it, we can tell it to go look for whatever we want to whatever we want for it to look for. And usually that's a protein of some sort. And we say, hey, go look for this, boom, go send it into the body, and it goes and it looks for whatever we want it to look for. So once we figure out how to do that, once we figure out how to send something in and target something, then we were like, all right, now we're in business. We can now send something to where we want it to go. Now, what's on these tumor cells that we can tell it to go look for? What can we tell these monoclonal antibodies to go look for? So, and attack. So then the race was on to find these targets. And so now is when I'm going to erase my board here, and I am going to do a little bit more drawing. Okay, so really use your imagination here, okay? You're really going to have to just stretch your mind and work with me here and what I'm telling you this is supposed to represent. Okay, so back to where we were. I said we were looking for targets on our cells, right? Okay, so first I should say that the way the human body signals is it uses proteins. Proteins are the signals. Proteins are like little flags. Proteins are the flags that it uses to signal everything. Hey, I'm over here, come do this, or it sends a flag over here to do this, or to do this, or to do this. So proteins are what we're looking for. So I've used flags here on this cell to represent proteins. So basically, for targets, we're looking for proteins, and proteins are the signals that tell cells to do everything. They signal all the steps in any kind of process that needs to happen. So if there's some kind of process that from start to stop, there needs to be a protein that tells it each little step of the way. So you can target little steps in that process. Look for the little protein that tells it to do one step. Go for that one, yank it out and see if you can mess up that pathway. So if you hear people talking about looking for pathways, that's what they're talking about. They're looking to disturb a pathway, disturb something that's happening, a process that's happening. So we start looking, early 2000s really, well, we were looking earlier than that, but we started getting some success at looking for targets in the really early 2000s, and we were going, okay, what's on a tumor cell that is probably not going to be on other cells? What can we find? And that's the real trick, you know, again, here we are. We're looking for things that we're not going to find on other cells that are just going to be unique to tumor cells. Well, tumor cells, you know, we said they're rapidly dividing. Well, so they're rapidly dividing, they're growing quickly. So as you can imagine, they're also kind of like teenage boys. They're growing so fast, they'll eat you out of your house, right? They're just going to stuff themselves all the time. They're eating all the time. Tumors are just like that. They need constant food. They need to be fed all the time. And because of that, they get really good at building themselves a good old vascular supply. They build their own blood vessels around them to bring in blood so they can just gorge themselves and have plenty of blood and be fed, and just so they can expand and take over their area. So tumors are very vascular. They have all these blood vessels and they grow and they have all these blood vessels around them. And so one of the first drugs that I actually worked on early 2000s was one of the actually first successful things was Avastin. You may have heard of it. We still use it now. And what it targeted was a protein in the pathway along the little process that these cancer cells would take to build these blood vessels. And we thought, oh man, we got it. We're going to mess up this process. We're going to stop this process. We're going to make it so that these cells can't have their blood vessels. We're going to cut off their food, starve them. They're going to die. We're going to cure cancer. And we thought we had it. And our trials went well. And this drug got approved. And it did help. But what we figured out, though, was that once we were able to shrink the tumor down to about 1 centimeter, then our drug wasn't able to really find those cells anymore. So you can only get so far. So then we're like, okay, well, this helped, but it didn't completely get rid of it. And that's a lot of what we have seen happen with a lot of these targeted drugs. You can get these tumors to get down to a certain size, but then you just can't completely get rid of them. So we keep looking. And so a lot of those early targets were things that we were looking for that just kind of were parts of the cells that we thought helped to keep the cells alive. Or this is this little boat that I drew. It's kind of supposed to be representative of sometimes there's some signals that these tumor cells send back and forth between each other, and they have to communicate with each other to stay alive as a group. And so we would target some of these cells, or some of these, proteins, these little flags on these proteins, and go knock out some of their communication there and say, all right, we're going to do that. Now y'all can't talk, and then you're just going to die alone. That worked a little bit too. Got some success there, but didn't do it completely. So we keep going after the numbers of targets we've gone after over the years, hundreds and hundreds. And some of them have been successful, some of them less so. And I mean, I can't even tell you how many. And there's so many of them that the process on paper makes complete sense. And then when it gets into the human body, it just doesn't work. This is the thing about science that can be maddening. It's never predictable. And when you talk about what's supposed to happen in the human body, things that are supposed to happen in the human body, whatever. Yeah, right. You can never predict what's going to happen inside the human body. There's so much we don't know about it. So anyway, as we move on towards the present, we started to recognize more and more how important the immune response was, until we get closer to now, when we got to the point where we are starting to realize, wait a minute, half of this whole ball game really is that the immune system is just going on by and letting these cells do their own thing, right? So we're going, okay, we need to ramp up the immune system, was the initial thought. Well, hey, guess what? You can't do that, like I mentioned in the last video. Ramping up the whole immune system, bad idea. You ramp up your whole immune system will kill you. So you can't do that. So we tried a little bit of that and got very early on figured out that was a bad plan. So the idea that your whole immune system is depressed, while that may be the case in some people, even if that's the case in some people, if you try to tweak the immune system and turn the volume up, so to speak, on all of the aspects of the immune system so that they start targeting things that aren't supposed to be there, it just gets out of control, and then your body starts attacking itself. Because the other thing, remember, these cancer cells were once normal you cells. They're human cells. They were normal cells in your body before, and they're still human cells. So you're trying to get your immune system to attack your own cells, but at the same time, tell the difference between you monster cells and you normal cells. So it's tricky. It's not quite that simple. So there are markers on your cells that show the body that they're your own cells. They're called MHC cells. And a lot of these cells still have those markers. At some point they lose them sometimes, but a lot of these cells still have those markers, and they still say, hey, I'm a me cell. I'm me. Don't bother me. I'm one of you. We're the good guy. And that's part of the problem too. So it's very, very difficult here. It gets so tricky. It's kind of like a spy game or something, right? So we move along. So we figure, okay, we can't turn up the whole immune system. We can't turn up the volume everywhere. We still got to go back to this target, this area, right? Okay. So then we learned that there's this muck, I'm going to call it, not the official term, muck that kind of surrounds the tumor cells. The official term would be the tumor microenvironment, and there are chemicals called cytokines and things, but we're just going to call it muck. And we're going to act like it's kind of like a mist that's around the tumor that gives the tumor extra power, and it slows down anybody that comes and tries to attack it. It feeds the tumor, it makes the tumor strong and healthy, but it slows down anybody coming from the outside that tries to come in and attack it. So this sludge we started realizing, okay, there's some of these chemicals in here, let's go after some of these. So we did that, some of that was somewhat successful. Again, not entirely successful. So you see how this goes? This is not an easy thing. This is slow. It's a hard, long slog. So next up, we've still been at the drawing board this whole time with the immune system. So we're like, okay, now what do we do? And then we had this big discovery in the past 4 or 5 years. I'm sure you heard they even got, I listened to NPR, and there are even some commercials on NPR about this. So-and-so that discovered the PD-L1 pathway. Well, this was a big deal. Okay, so what we discovered, and this is a really big one, was the PD-L1 pathway. PD-L1 is one of 4 proteins that are what we call checkpoint signals. And basically, here's the idea. They're like little guards that are holding up flags. And these are the purple ones I drew right here. What these flags say are, don't eat me. So these are PD-L1s, these purple ones right here. They're flags, they're stuck on the outside of the cell, cancer cell, and they say, don't eat me. And what happens is the immune cells come along that would normally destroy bad cells. They see these purple PD-L1s that say, don't eat me. And they say, oh, they're very obedient immune cells. They say, okay, I won't eat you. And they keep on going. So we figured out how to take remember that monoclonal antibody, our search and rescue dog? We took our search and rescue dog and we said, hey, go find PD-L1 and go. Send it into the body. And we thought, oh, this is going to be it now, because we can, this PD-L1 is on almost all tumor cells. We just send it in there. We knock these suckers out. Our search dog is going to go take them out. And now there won't be any don't eat me flags. And then the immune system, next time it comes around on its nightly search or whatever, it won't be there, and it's going to eat all the tumor cells up. It did work for some people, but it turns out only about 20% of all cancers have these PD-L1 flags on their surfaces. And so what we do now is we test for that. We can take some of your tumor and we can run tests on it to see if those little PD-L1 flags are there. If they're there, then we have some of these drugs that you see the commercials for, all these lovely commercials on TV, then you can get those drugs. It so far hasn't been like a magic wand like we had hoped. It hasn't completely wiped out the tumor in those people. There still seems to be some other kind of thing. We think maybe this tumor muck that's around it still kind of slows down our bloodhound, our search dog, when it's trying to get to our flags here. Something's going on. There are other things that are happening. It's not a one-step thing. There's a million things going on. So we've only figured out one little step, but it does seem to help a lot in those patients that actually have that. And so there are 4 drugs on the market right now that have these particular flags that are in this category of checkpoint inhibitors that are don't eat me flags. So these are the ones that you're seeing all these commercials on right now, that everybody's talking about this immune therapy. It's a big deal, and oh my gosh, this is great. And this is a big deal because this is one of the first times we've successfully been able to really manipulate a piece of the immune response that's just in the area of the cancer cell. So this is huge. So we're like, oh, here we go. This is awesome. This is what we've been looking for. We've been trying to manipulate the immune system, but just in a little area so that we don't mess up the whole body. So that's why that's a big buzzword right now. You're here, you probably have heard, or if you haven't and you start reading up on cancer, you're going to see PD-L1 somewhere, because PD-L1, CTLA4, PD-1, and there's several, there's another one, and it's like all 4 of these are these checkpoint inhibitors, and these are the ones that we have successfully been able to target with our monoclonal antibody, and they're the ones that have these don't eat me flags. So that's the big deal there. Now, we're still looking for all kinds of other targets. We're looking for all kinds of stuff. Now, we've got other immune things we're doing. We've got vaccines. We have, and we were doing trials where we're taking some of the people's tumor out, killing it, and reintroducing it into the body and trying to get the body to recognize it just like it would a virus or a bacteria and build up immunity to it that way. We are trying all kinds of things, but the biggest thing that we are doing right now, and this is happening in hundreds and hundreds of labs all over the country and all over the world, is we are looking for targets that we can send our search dogs after in the body, and we can interrupt. Now, I will mention real quick, a lot of people have asked me about PARP inhibitors. What are PARP inhibitors? You see my little tiny lines here. PARP is a protein that's in the middle of a pathway, and I kind of liken these pathways sometimes to like a set of dominoes, because you've got to have all your dominoes in a line and they've got to all fall over to make something happen, right? Well, the PARP pathway is a staying alive pathway. I kind of hear that song every time I hear it, that staying alive pathway. And it's inside the cells. And if you take away or knock out PARP, then this process that helps keep the cell alive is gone. And the cell loses this kind of like superpower that helped it stay alive. So it's the staying alive property that PARP gives the cell. It's not a great analogy. I don't have a really good analogy for that one. It's so complex. I've thought a lot about that one. I'll come up with a good one, and maybe I'll re-record this at some point. But PARP is a part of a pathway that gives the cell kind of like a staying alive superpower in some kinds of cancers, particularly cancers that have the BRCA gene. And a lot of those are female cancers. Those are the ones that really seem to have that staying alive pathway inside the cancer cells. And so that's why you hear of a lot of the PARP inhibitors, which would be drugs or those search dogs that can go after the PARP. They're used a lot in things like ovarian and some other female cancers. So basically, any of these targeted drugs are going to be something that we found a target somewhere on the cell, in the cell, around the cell, something in the environment of the cell that we think we can go after and disrupt, that we think will be fatal to the cancer cells. And that's what a targeted agent is going to be. And so our hope is, though, that we're going to be able to target more immune things like these checkpoint inhibitors, like this PD-L1 flag that we have been able to target. If we could find something like PD-L1 on everybody's cancer, then that would be a good foothold to have. That would really weaken everybody's tumors, and that would be a big step for everybody. Now, here's the problem. Now, you might be getting an idea here of one of the things I keep coming back to somewhere in every video, which is everybody's tumor cells have different flags on them. All the different colors. They're all mixed up. Nobody's tumor cell is exactly the same. So the drugs that are going to work on your tumor are not going to be the same drugs that are going to work on other people's tumors. There might be one drug that works in most pancreatic tumors, or one drug that works in most breast tumors, because it may be that most breast tumors have this one, but some of them have the blue one, some of them don't. Some of them have an orange one. Some of them have a yellow one. I mean, it's almost like a fingerprint. So there's a test that a lot of people have done, the foundation test, where they take a piece of your tumor and they just run a whole slew of tests, and they're looking for targets. They're looking for all these flags, pretty much all the flags we know about that we can target. And they just run the whole slew, and they look. And they just report whatever they find that's on your tumor. And that way they can say, okay, what do we have a drug for that we can go after? That's what that foundation report is about. So, you know, it's really hard. This is why I keep coming back to why we don't have a cure for cancer, because cancer is not one thing that's the same from person to person. It is very different. It's very complex, and it's just, it's tricky. It's very tricky. So after viewing my video, I decided I needed to come back in here and add a little ending segment, because it was sounding a little depressing there, sounding like we were never going to get anywhere in cancer because it's so difficult. And yeah, this stuff is hard, but I want to remind you, hey, cancer is not a death sentence for everybody anymore. Many, many years ago, sure it was, but society needs to get over that mindset. Cancer is not a death sentence for everyone anymore. We get rid of cancer for many, many patients. And that's especially true if your cancer is local or regional, which basically means your cancer is where it was originally found or in the lymph nodes around the area. That's when cancer has got the best shot of being taken care of. I didn't say cured. In the scientific and medical world, we don't like that word cure. It's just not, it's kind of a hokey word to us. So we kind of cringe when we use the word cure, but I guess I could say it. I'll say it. Yes, many, many people these days are cured of their cancer with a combination of the treatments I talked about in my last video and some of these targeted agents, or just, there's all kinds of combinations of that. And of course, like I said in the last video, depending on what kind of cancer you have, it's, you know, we mix it up, we do all kinds of different things. And many, many people are cured of their cancer these days. Now, when it gets super hard and really tough to treat is when cancer spreads to other parts of your body. We call that being metastatic. That's when cancer is hardest to treat. Now, these targeted agents, like I said, they're helping and they're improving responses and helping to get rid of cancer in all stages, you know, from early cancers on up. But where they're really kind of changing the game for us is in these metastatic disease cases, or these cases where patients have cancer that's spread to other parts of the body. What these things are enabling us to do more and more is change cancer more into something that's like a chronic disease. So it's making it so that we can prolong people's lives. They're able to have a good quality of life, or at least a decent quality of life, and take these drugs and keep on going and going and going. And so that it turns it into, instead of being an, oh my God, you know, immediate emergent kind of disease, to a one that you deal with as though it's a chronic illness and you just keep going with. And it's a whole mindset change that society is going to have to start dealing with, because this is becoming more and more the way things are going for those patients that have metastatic disease. That's just the way it is right now. That's what a lot of these targeted agents are helping us to do. And believe me, that's a big improvement. That's a huge thing. I mean, you'd much rather have a chronic disease than something like what everybody used to think of, oh, you're about to drop dead. But back to what I wanted to say is that cancer is not a death sentence for everyone anymore, and we get rid of cancer in many, many, many patients. So that's all I just wanted to say. And please remember to like and subscribe. I'm going to point so that you remember to go down there and click on that little button down there. And that's it, and I'll be putting up some more videos. Thanks so much. See you later.